This lecture is on properties and trends in standard molar entropy, or S. It is important that one knows some information about S. Unless otherwise, temperature equals 298 K. The 5 factors that will be investigated in this lecture are physical states, phase changes, temperature changing, dissolution of a solid or liquid in water, dissolution of a gas in a liquid, and atomic size molecular complexity. When performing a phase change, heat is either absorbed or released. Example 1. Melting, vaporizing, or subliming requires heat to be absorbed, and as a result, there is an increase in freedom of motion and thus an increase in entropy. Example 2. Freezing, condensing, or deposition crystallization releases heat, and as a result, there is a decrease in freedom of motion and thus a decrease in entropy. Reminder, as a result, gases are far greater than liquids, which are greater than solids in freedom of motion. Here is a figure showing the 3 states of matter: solid, liquid, and gas. When a substance goes from solid to liquid or liquid to gas, entropy increases because the particles have more freedom of motion, and as a result, the amount of disorder also increases, resulting in delta S greater than 0. Here is an example where we have 3 substances, Na, H2O, and graphite, as solid, liquid, and solid. When all substances convert to gas phase, entropy increases. Here is a review exercise for you to work on. Which substance do you expect to have the larger entropy value? Gaseous iodine or solid iodine? Temperature and entropy are proportional. As temperature increases, entropy also increases. The reason is because as temperature increases, heat is absorbed and kinetic energy also increases, which leads to an increase in microstates and thus an increase in entropy. The left figure shows 2 different temperatures, T1 and T2. At T1, most molecules will have a small amount of kinetic energy over a small region. But at T2, the amount of kinetic energy will increase over a large range, resulting in an increase in entropy. The right figure illustrates the 3 states of matter, where it illustrates that entropy increases from solid to liquid to gas phase. Here is an example involving copper at 273, 295, and 298 Kelvin units. By looking at the entropy values, an increase in temperature results in the entropy increasing. Here is another review exercise for you to try. Which temperature will have the larger molar entropy value? Why? Water at 90 degrees Celsius or water at 5 degrees Celsius? If you take an ionic solid and dissolve it in water, the entropy increases due to the presence of ions in solution, which will lead to more freedom of motion compared to its original form. If the solid is a molecular compound when dispersed in water, the change in entropy is minimal at best. Here is an example of NaCl or sodium chloride and CH3OH or methanol. There is a larger difference in entropy from solid NaCl to aqueous NaCl because in solution there are two ions present in water, increasing the entropy of the system. In comparison, methanol is a molecular compound that, when dispersed in water, it still remains as one unit, and thus there is a minimal change in entropy when going from liquid to aqueous solution. When a gas dissolves in a liquid, there is a loss in freedom of motion, resulting in a decrease in entropy in solution form. For example, let's compare oxygen in the gas phase versus oxygen in aqueous solution. The standard entropy of O2 gas equals 205 J per mol K compared to 110.9 J per mol K in aqueous solution. The reason is because since the gas's kinetic energy decreases when dissolved in liquid water in forming its aqueous solution, this order also decreased. Note, if a gas dissolves with another gas in forming a solution, entropy increases due to separation of and mixing of the molecules. If the elements are within the same group, the larger the molar mass, the more microstates present. The larger the molar entropy. In this example, there are 5 elements in group 1A from Li to Cs, where as molar mass increases, the entropy also increases. For different forms of the same element called an allotrope, the entropy is higher in the form that allows the most freedom of motion. Here is an example between two allotropes of carbon, diamond and graphite. The reason graphite has a higher entropy over diamond is due to freedom of motion. Diamond is a three-dimensional figure with a shape of tetrahedral, whereas graphite is two-dimensional on a flat plane and has a shape of trigonoplanar. Since graphite has more freedom of motion, entropy increases. For compounds, entropy increase with chemical complexity or number of atoms in the formula. The table below features 3 compounds, NaCl, AlCl3, and P4O10, and 3 nitrogen oxide substances, NO, NO2, and N2O4. As you can see, the more atoms present, the higher the entropy value. The different movements molecules may perform include vibrational motion, rotational motion, and translational motion. Here are 2 structures in the ball and stick model, nitrogen monoxide and dinitrogen tetroxide. As evident here, dinitrogen tetroxide has more atoms than nitrogen monoxide, resulting in more vibrational motions, resulting in an increase in entropy. Larger compounds such as hydrocarbons, these substances must also consider the motion of different parts of a molecule. Entropy increases with chain length. Cyclic rings of similar molecular forms have lower entropies than their corresponding chains due to a restrict freedom of motion. Lastly, when comparing gases to liquids, for example, the physical state dominates the effect of molecular complexity. In this pair of structures, we have methane on the left and ethane on the right in the ball and stick model. Ethane here has more atoms in its structure and is longer in carbon chain length. Entropy increases with chain length. In this pair of structures, we have cyclopentane on the left and one pentene on the right in its ball and stick model. Although both structures have the same molecular formula, one pentene has a larger entropy value over cyclopentane because entropy increases with the chain over ring due to freedom of motion. A ring structure has a restriction on freedom of motion in comparison to one pentene, which is a chain and has more vibrational motions it can undergo. This is another review exercise for you to try. Determine which substance has the higher entropy in each pair. Assume constant temperature unless otherwise stated, and explain your choice. A, 1 mole of P2O3 gas or 1 mole of P2O5 gas. B, 1 mole of SO2 gas or 1 mole of SO2 solid. C, 3 mole of O2 gas or 2 mole of O3 gas. D, 1 mole of NaCl solid or 1 mole of NaCl aqueous. E, water at 20 degrees Celsius or at 100 degrees Celsius. F, 1 mole of CCl4 gas or 1 mole of CF4 gas. For the remaining part of this lecture are solutions to review exercises or problems. Please view only after completing these exercises.